Hello, AP Chemistry, and welcome to the auto ionization of water and calculating pH. So, first of all, water auto ionizes a tiny, tiny amount. Yes, tiny, tiny amount. Because we know, right, that in neutral water, the amount of hydrogen ion or hydronium ion is equal to the amount of hydroxide ion, and the product of both of these is equal to 1 times 10 to the negative 14th, which means that the concentration of each of these is 10 to the negative 7th in neutral water. Yes? Which means that it auto-ionizes, right, 10 to the negative 7th molarity, basically. Yeah? Does that make sense? Okay, which means it auto-ionizes some, but very, very little, which goes back to what we talked about sophomore year, in that pure water has very, very little conductivity, okay? Because there's very, very little ion present in pure water, okay? Which is different than like tap water or seawater or anything else, or pool water for that matter, okay? So, anyway, water auto-ionizes, producing some hydroxide and hydronium. Now, water, because this is all aqueous, basically governs the relationship between hydroxide and hydronium for any aqueous solution. Which then means, right, that if we're talking about an acidic solution, we're always talking about hydronium being greater. If we're talking about a basic solution, we're talking about hydroxide being greater. But because it's aqueous and water is present, right, it's still all governed by the fact that hydronium times hydroxide has to equal 1 times 10 to the negative 14th. Okay? Which then gives us a little bit of a little bit of flexibility in our math, okay? Because we know then, right, if pH is equal to the negative log of my H3O plus, right, then I know that, for example, POH is equal to negative log of my hydroxide concentration, right, which then also means that pH plus POH equals 14, right, or H times OH minus equals 1 times 10 to the negative 14th, right? And this going back to the properties of logs, yeah? Now, important to note, right, that log scales go on a base 10 system, right? Which means that the difference in one pH unit is a difference in an order of 10 difference, yes? One pH unit is an order of 10 in terms of difference in concentration, right? So, for example, stomach acid, right? Approximately 1 times 10 to the negative 1, right? Which is a pH of about 1, right? So, see? 1, negative 1, yes? Does that make sense? Right? Because if I do the log of 10 to the negative 1, I get 1, right? 10 to the negative 1 gives me this, yes? Basic properties of logs. All right. Lemon juice has a concentration of about 10 to the negative 2, right? Where negative 2 gives us a pH of 2, right? pH unit, 1 difference. Concentration is a difference of 10. Yes, that's what logs mean, right? So when we say that something has a pH difference of 1 and we say it's not a big difference in pH, that's not true, right? Going back to that discussion from the last test where you guys all talked about 9,000 joules as being a giant amount, right? But it's not, because joules is not the standard unit of measure. Here it's the same thing, right? If you were going to talk about stomach acid and lemon juice have approximately the same concentration of H plus because they have approximately the same pH, not true at all. Yeah, does that make sense, right? It's an order of 10 difference. We would have to dilute this 1 to 10. We would have to take lemon juice, no, sorry, wrong direction. We'd have to take stomach acid and basically take 10 mils and dilute it to 100 mils to get the same concentration in lemon juice. Yeah, does that make sense? Tenfold difference in concentration. Okay. Anyway, so we have that, right? And then, and you should know some of these, right? So stomach acid, pretty acidic, right? Which makes sense because it literally breaks down food. And if it ends up in your esophagus, it burns away at your esophagus, right? Makes sense. It's acidic, right? Vinegar and Cokes tend to be somewhere down here, right? Between a pH of 3-ish, right? Which again makes sense, right? Because vinegar is commonly used as a cleaning agent, right? Vinegar, for example, if you get that white buildup on your guys' like sinks and shower heads and stuff from water deposits, right? Which are basically metal oxides, which are basically anhydrous bases. Then we can use some vinegar, which is an acid, right? To sort of eat away at those things, okay? Tomatoes, right, are relatively acidic, which is why depending on the type of cookware you use, right, you don't cook pasta sauce in any kind of cookware, right? Coffee though can also be a little bit basic. Coffee has a lot of different flavors in it, which is why coffee is such a that's why people talk so much about the flavors of coffee, right? Because there are so many flavor components there. Rain, saliva, milk. So if you look here, right, all of these are our sour things, right? Bases tend to be bitter. Things that are bitter are basic in general in terms of flavor. So blood, you should know what that is, approximately 7.4, right? Seawater is a little bit basic, courtesy of some of the salts that are dissolved in it, which again, we'll talk a lot about that later. Borax, lime water, household ammonia, right, which is often used as a cleaner, is way down here on our basic scale, right? So approximately 12, which again tends to negative 12 in terms of hydronium ion concentration, which by the way, if we flick to this other side, right, if this is 12, this has got to be 2. Yes, does that make sense? Going back up here, if this is 1, this is going to be 13. Going to hydroxide versus hydronium, yeah? All of these things are related. Bleach also somewhere around here, right? So anyway, pH, super duper important. Okay, couple of quick samples. So in a sample of lemon juice, if my H plus concentration is this, what is pH? That one's really easy. Yes, we're just going to take the negative log base 10 of that. Okay. Commonly available window cleaning solution has hydroxide ion concentration of this. What is the pH? So what are our options here? Right, I could take this and I could calculate POH, right? And then I could do pH plus POH equals 14, right? Likewise, if I wanted to, right, I could take my 1.9 times 10 to the negative 6 times this is equal to 1 times 10 to the negative 14th, right? Solve for my hydronium ion concentration, right? And then plug that into my pH equals the negative log of this, yes? Either way gets you the same answer. Either way is approximately 2 steps. Doesn't matter which one you prefer. It's totally up to you, yes? All right. Just be mindful. Try not to round until the very, very end. And do be mindful going back to your textbook, right? The rule for sig figs versus logs, right? When we take the log of something, right, since we're changing its scale so much, when we take the log of something, only the decimals count as sig figs, right? So if I say that something has a pH of 1.23, only these count as my sig figs, right? Which means that, so for example here, this has 2 sig figs, which means that I would report my pH as something with 2 decimal places. Yes? All right. A solution formed by dissolving an antacid tablet has a pH of this. Calculate OH. So that goes back to what we talked about up here, right? This is my pH, which means that this reflects my hydronium ion concentration. So if I want this, right, again, I will take one of these 2 routes to get there. Does that make sense? All right. Next up, measuring pH. So one way we can measure pH is with a pH meter, right, where we have an electrode that needs to be submerged in the solution, right? And it connects here, and basically based on how much conductance this probe measures, that gives us a measure of how much hydrogen ion is present in my solution. Okay? And that gives us a relatively accurate measurement, right? This one goes to 2 decimal places. A lot of them do go to 2 decimal places. Now, the quick and simple, though less accurate measuring of pH, right, would be to use an indicator, where indicators have different colors at different pHs. Now, the reason that these have different colors at different pHs is because they themselves are weak acids or weak bases, right? Meaning that, so for example, here for phenolphthalein, right, we get a pH shift right around 8 or 9, right? So if we look at phenolphthalein, around 8 or 9, right, is its pH shift, which means that at pHs less than that, that species is protonated. At pHs higher than that, it's deprotonated. So it's basically 2 forms of the same thing, and those 2 forms have a different color, right? So here for bromo blue, right, for bromothymol blue, at pHs of less than 7, I should have drawn my line here actually, right? At pHs of less than 7, it's protonated, and that protonated color is yellow. Here it's deprotonated, and deprotonated is blue, right? Likewise up here, right? We have protonated is pink, deprotonated is yellow. Now, this brings us back to equilibrium concepts, right? In terms of why this one is green, right? This one is green because if the deprotonated is yellow, protonated is blue, but we have a mix of protonated and deprotonated, we end up with something that's green, right? Likewise here, if protonated is clear, deprotonated is pink. In between, we're going to get a pale pink if we have a mixture of both of those species. Yes, same thing up here. And again, we'll talk a little bit more about that when we get into the acid-base section, or weak acids and weak bases. But that's how all of these work, basically, which is why when we use them in solution, we use a tiny, tiny amount, because that tiny, tiny amount isn't going to affect the overall pH of our solution, okay? But it's going to be enough to give us a read on our pH. And note that here we're talking about an entire pH unit, which, going back to concentration, right, is an order of 10 in concentration, right? Which is why this is definitely far less accurate, but depending on our purposes, sufficient for the job. All right. Thank you for listening. Be good, and I will see you guys soon. Bye.